So, so colliding black holes and gravity waves. Okay, so pretty much every crazy extreme concept in physics and gravity is involved in this discovery. So let's take it a few steps at a time. So this picture shows you, of course, in white dots, two black holes that are about to collide, and a schematic representation of the gravity waves they set off on the fabric of space-time. So what does that mean? Let's unpack that a little bit. What is a gravity wave? Let's start with waves we are familiar with. So if you throw a rock in a pond, you set off ripples. These are ripples on the surface of water. You're also familiar with radio waves that your antenna can pick up. And these were generated by electrons that are oscillating. And they trigger waves in a more abstract field of electric and magnetic fields. Similarly, when you have orbiting masses, and the more compact and the more rapidly they're orbiting, the better. When you have these, you trigger waves in space and time itself. They're very subtle, but we've now discovered them as Einstein anticipated nearly a century ago. So, what waves? What does that even mean? With water waves, you know that the surface of a pond moves up and down. So the wave propagates. If a boat is moving by or you've thrown a rock in, a wave propagates outward, but everything that's on the surface moves up and down. So that's the nature of a propagating wave. With gravity waves, the story is a little subtler. Again, you need a trigger, such as even the Earth moving around the sun. They're orbiting. On top of the orbit, if they jiggled a bit, you would definitely trigger these propagating waves that go out at the speed of light. And the thing that's waving is just the medium itself, space and even time. So if you were on the path of this propagating front, the time that you measure would get dilated, squeezed, dilated, squeezed. And similarly, space would dilate and squeeze. So your face would go like this, squish, like that. It's very, very subtle. That's why we had to wait for decades of technology and for the biggest things that we can find, large black holes, to be able to measure this. The energy that's triggered, even by the Earth and Sun, is like a millionth or much less than a millionth of the energy that you pick up with your radio antenna. This is what you'd see if you had a super Hubble telescope and you had two black holes that collided and merged, like the LIGO experiment saw. But in the center, there's these two black holes that are orbiting each other. They do their death spiral, and then they merge to form one black hole. Okay, so this happened over 20 seconds. The observations that were made, this happened over a fraction of a second. So what you saw there wasn't actually gravity waves. It was the background images that were distorted by the black holes as they fell in. So let's look at what the signal would be like. When two black holes spiral in towards each other, so these are meant to be black holes bigger than the mass of the sun, then this whole stretch is less than a second long. And so you imagine two black holes that are bigger than the sun, whose event horizon, their outer boundary, is somewhat bigger than the size of Philadelphia. And they get close enough that they then cannot but lose energy and spiral in towards each other and merge. When they do that, we can detect gravity waves, even when they're a good part of the observable universe away from us. The gravity waves reach us, and their period of oscillation is related to the period of the orbit. And then when they merge, then the event horizons of the black holes themselves merge. And so that's the closest glimpse one can currently hope to get of a black hole. And then you get this rapid pattern. And then they gently settle down into a stable black hole. This picture, roughly speaking, has been known to theorists for a long time. And in the 70s, this heroic team of scientists at Caltech and MIT had this dream to build a detector and measure this. So they started, the National Science Foundation funded them, and they said, we need actually another decade to do it, then another decade to do it. And each of these decades, the NSF had the vision and perseverance to keep funding them at the tune of millions of dollars a year. So how does the detector work? So when a gravity wave passes, it's compressing and expanding space itself. Very, very little. So the way this detector works is you have two mirrors that are bouncing laser beams back and forth. And when a gravity wave passes, it pushes the mirrors apart, and they're suspended using an elaborate contraption so that when they get pushed apart by the gravity wave, nothing else holds them in place. The way it actually works is this length is 2.5 miles. So there's a vacuum tunnel, one in Washington State, one in Louisiana. And there's another one perpendicular to it. So the gravity wave first expands this one, then this one again, then this one again. And by cross-checking the two, you create an interference pattern. This story is complicated. It's a story of technology, really, because the shift you're looking for is much smaller than the size of a proton. And you look for it over a laser beam that's traveling 2.5 miles. It's unbelievable, even to a physicist, that they did it. But they measured this thing in these two very different locations, and they measured it with a time lag that was exactly the time it takes for a gravity wave to travel from one to the other. So although there's 1,000 things that could have produced this slight shift, including the sneezing of a graduate student, they had all the checks and balances in place to conclude that it was a gravity wave. And this is the data. So if you remember, this is the pattern that theorists predicted colliding black holes would produce. And this is the first detection. For those of us who work on trying to detect subtle things, it's a dream for the first detections to be so clear that even by eye, you can see this pattern is the same as that theoretically predicted one. Usually you have to massage the data beyond recognition to pull out a subtle signal. But in the pre-dawn hours of this September morning, two extremely tired young, I think a postdoc and a graduate student working the shift, saw this, and then they did like 100 different checks before they announced it to the world. And it was evident very quickly that this was the result of the collision of about 30 solar mass black holes, 29 and 32 solar masses. The whole thing took less than half a second. The most interesting piece was less than 1/10 of a second, where the event horizons coalesced. And this happened in a galaxy 1.3 billion light years away. Okay. Since this event, they have detected a couple of others, not quite as dramatic as this one, but we are all convinced their experiment is working. They're going to be recording a bunch of these events, like dozens in the coming years. So what are we going to learn from this particular experiment and others that are going to come after it? We're going to learn about strong field gravity. What happens near the event horizon of a black hole? We've known that black holes exist through a number of compelling but indirect pieces of evidence. Now we are seeing the most direct piece of evidence one could hope for, and we are seeing what happens right at the event horizon. So far, in case you hadn't heard, Einstein's gravity passes the test. There's nothing in that curve that shows any breakdown of Einstein's general relativity. We're going to see a lot about black holes and neutron stars. How many of them come in binaries? That's something we hadn't known. But only in these binary systems do black holes give gravity waves like this. And how often do they get close enough that that death spiral becomes inevitable? One big question that many of us are pursuing is what happens once you have gravity waves? This black hole is living in a galaxy. It's surrounded by gas and stars. Once in a while, a poor star is going to get caught up in that death spiral and get tidally shredded. And when it does that, it's going to set off bursts of X-rays or gamma rays. So this is one of the big quests, to find electromagnetic counterpart in light or gamma rays that accompany the black holes, because right now we don't really know where on the sky it is or which galaxy it's living in. And we'd love to be able to pinpoint that. More ambitious quests for both LIGO and a successor experiment in space called LISA is, can we see gravity waves from the early universe? You know, the pre-Big Bang universe was believed to contain a background of quantum fluctuations, and as part of that, gravity waves. So we'd love to be able to detect that background, but that's a ways into the future. Some of our colleagues are already pursuing some slightly exotic signatures where the event horizon of a black hole isn't like a super thin boundary, but it has some structure that is predicted by theories of quantum gravity. So those would also produce an echo in that pattern that I showed you. So this is only a sampling of the kind of interesting questions that we hope to be able to address once we get a dozen or so of these events coming in every year. Other than gravity waves, we've been pursuing black holes for decades. So this is the neatest picture of pursuing a black hole that I know of. It's in the center of our own galaxy. Right in there is what's called Sagittarius A star, a black hole that's between 3 and 4 million times the mass of the sun. And these are the orbits of stars going around it. The dots are actual observations, and the curves are completing the orbit using Kepler's laws. So although some of these stars go really close to the black hole, it's still 1,000 times the event horizon. The closest passage is actually going to occur in the coming year. There's a new experiment called the Event Horizon Telescope that's going to use radio telescopes to literally look at the shadow of this black hole. So it'll get much closer and look for this asymmetry that you expect in the black hole. So you've heard about quite an array of ideas and phenomena. I'm going to show you only a few more relatively straightforward pictures, I think anyway, and then we can take questions. So gravity waves, we talked about, are these dynamic things because space-time is expanding and collapsing. Gravitational lensing is a little different. It's a more static phenomenon. When you have a heavy body, Einstein's theory tells us it bends space. And so you can consider this heavy body and the bent space around it as just existing, and a light ray that's passing by will be bent by it. And so this is sort of the two-sentence version of Einstein's gravity and light. If space itself is curved, there's a deflection, whether it's light or a particle. And so the natural path near a heavy object is curved. And astronomers like me, we use the consequences of that. So one consequence is you see these beautiful Einstein rings. So this, for example, is a big elliptical galaxy. It's got 100 billion stars in it. And the faint blue ring around it is a much more distant galaxy that was a pretty run-of-the-mill galaxy, but was lucky enough to sit right behind this elliptical. And so it got lensed into this beautiful ring, which you can see only part of on this projector. So it only takes freshman math to figure out that the size of this ring gives you evidence for dark matter. That's one of the most direct uses of lensing. We can map dark matter. And we can then further ask, can we disentangle the existence of dark matter, which we can't see, from a possible change in the law of gravity, which we want to infer from the same data? So that's a fascinating little quest that we are on. Another way that we use lensing to map dark matter is to look at a whole galaxy cluster, which has got a whole bunch of galaxies in it, and we can use the distortions of the background images, the wallpaper, to figure out that it's filled with this dark matter halo shown in blue. So that's the effect of lensing behind special objects, galaxies and clusters. What we are doing right now at Penn is using a big survey to map dark matter even where there's nothing special. Or put another way, we are finding cosmic filaments, voids, halos of dark matter, and possibly even black holes just by how they affect light behind them. We're doing this with this dark energy survey carried out at a telescope in Chile, which is mapping the images of 300 million galaxies. We're over halfway through. And supernovae to learn about both dark matter and dark energy. So this is a map, the biggest map of the dark matter distribution that we produced a couple of years ago. It's 100 square degrees. The full moon would be about this big on this map. And the structures that you see are bigger than any galaxy or cluster. These are superclusters and big cosmic voids. This, for example, is the largest supercluster among the 2 or 3 largest superclusters that we know of in the universe. So we use millions of galaxy images to make this map. You can see it doesn't have very high resolution, but it does represent fairly the distribution of dark matter. And then we do a number of scientific applications with it. One of the applications that I can't resist telling you about, because we just finished the paper yesterday, is that we think we have found the edge of dark matter halos. So a galaxy or galaxy cluster would sit right in there. It's surrounded by this dark matter shown by the bright colors, represent the density of dark matter. And there's been a debate about whether around a known object the dark matter distribution has an edge or whether it just smoothly tapers off. And we made some measurements and believe we found this edge that we can then use because if gravity is stronger than Einstein's gravity, this edge would move inward. So because we found a relatively sharp feature, we can use it to test physics. Just note that we have seen how the secrets of how gravity works. They lie in observations of black holes, dark matter halos around galaxies and clusters, and as Mark described to you, the accelerated expansion of the universe itself. So we live in fortunate times since Mark and I left graduate school, a year we are not going to disclose to you. A dizzying set of discoveries and puzzles have emerged. And it's clear that they are pointing us to new physics that we've only just glimpsed. So it's fun to imagine what we might discover in another 5 or 10 or 100 years. Evidence of new physics, some theories that we might rule out, because some theories are easier to rule out than others. Thank you.